Okay, this is our second lecture on statics, and this lecture we're going to look at forces, and we're going to look at forces on a planar surface. And here what we do is we define a coordinate direction that is tangent to the surface, and we integrate along that surface. And then we also look at forces on curved surfaces, and we do this slightly differently by working out a force balance on a volume where this volume has this particular curved surface that we're interested in as part of its boundary, and we do a force balance on this volume and we use that to work out what the forces must be on our curved surface. This is much easier than defining a coordinate system that tracks this curved surface. Okay, so just to sort of remind ourselves about force and pressure, so force is a vector and pressure is a scalar. So if we've got an equation that says delta F is equal to P delta A must be a vector. So the area has a magnitude, obviously, and it also has a direction, and that direction is the normal to that area, and that normal defines the direction of the force, and the pressure and the area, magnitude of the area, defines the magnitude of the force. Okay, so when we have a surface that's horizontal underneath a liquid, we know that the pressure all the way along this surface is the same, and so it's relatively straightforward to work out the total force on this horizontal surface, because the integral becomes very easy. So we can see this at the bottom. So this is my definition for an elemental force in terms of the pressure at that point multiplied by that elemental area. And if we wanted to do the integral, we can say that P is equal to rho gz, and P doesn't depend on the area because Z is always constant. So if we integrate this equation, we can just write that the force is just the pressure on this particular plate multiplied by the total area. It becomes a little bit more complicated when we get to planar surfaces that are at an angle to the horizontal, because the pressure varies along the surface, and then we have to obviously perform an integral along this plate to work out the total force on this particular surface. And we do this on this slide here. So here, what I want, I've got a liquid surface here. I've got a plate here. So if you can imagine, I turn my plate 90 degrees so I can see it on my paper. Here it is. Has a funny shape. And what I want to do is I want to work out the total force on this particular funny shaped surface. Okay, so the way we go about this is we say, right, we need to choose an elemental area where the pressure doesn't change. So in this particular example, if I choose a small slice of this area, so this delta y is really small, and it's the width of the area at that particular point, I can say that the pressure in this little sub area is going to be constant, and so I can say that if I want to work out the small elemental force on this little sub area here, I can say that's equal to PdA, and the pressure is going to be equal to rho gh. So h is just the distance under the fluid surface of this elemental area, and I'm going to integrate along the plate surface, so I need to convert my h into y. So y is my coordinate direction that defines my planar surface. So I can do that by saying that h is equal to y sine theta, and I end up with this equation here for my elemental force. And then if I want to work out the total force on my plate, all I have to do is integrate all of my elemental forces. So I do that here, and then I think about this and I say, well, the density is constant, so I can take that out, and gravity is constant, so I can take that out, and sine theta is constant because it's a planar surface, so I end up with this equation here. Okay, and the general way to do this is effectively the definition of the first moment of area. So you probably get this from solid mechanics. So this y bar is my first moment of area, and this integral of y dA is just my first moment of area multiplied by the total area of my thing. So we don't need to do this if it's a simple shape. So for instance, if this was a rectangular plate of width w in this direction, then I could say that dA is equal to w dy, and then I could integrate this thing directly. But in the general case, it's a funny shape. You'd have to know what the first moment of area was, and then you can work out the total force on the plate. Okay, and if we wanted to work out the average pressure, if you like, so this is the pressure, this is the force on the plate divided by the area of the plate, so that's what this pressure is here. And the question is, well, where could this pressure be said to act? So if you can imagine that this dotted line, the y-axis, was a boundary, and on this side of the boundary there was a fluid, so this might be water, and on the right hand side of the boundary there's nothing here, so it might be air. So this force is acting in this direction because of this fluid of certain density, rho, and where, you know, and I have to balance this with a single force on this side to ensure that my plate doesn't move, because remember, this is a stationary problem. So I need to find out the point at which this force must be said to act on this surface to balance this distribution of force on this side. And to do that, we have to work out where the center of pressure is, and to do that we have to take moments. So this is how we would do this. So this is the force distribution that I worked out on the previous slide, and this is the total force that I worked out on the previous slide, and I need to balance this with this force acting at the center of pressure, and that will balance this force distribution I have on this side of the plate. So what we're going to do is we're going to take moments about this pivot point 0. So if we want to work out the anti-clockwise moment, we're working out this force distribution here. So what we have to do is we have to work out our elemental moment distribution. So if we take this particular force acting at this particular y distance y, this y df would be the moment at this particular point. And we can work out a whole series of these elemental moments, and then we could integrate them to work out the total moment on this side of the plate. And this is what we are doing here. So here's my elemental moment, and my force is the pressure times the elemental area, and my pressure is equal to rho gh, and I convert my h into y sine theta, so I end up with my elemental moment equal to this thing here, and then if I want to work out my total anti-clockwise moment, so that's the moment acting in this direction, I integrate my elemental moments, and I can take rho g sine theta out because that's always constant, and I end up with this integral, and to do this integral I have to know how dA depends on y. And this moment must be opposed by a clockwise moment, and this clockwise moment is F. So this is F is what I worked out from the previous slide. This is the total force on the plate, and this YP is my center of pressure. Okay, so I can end up working out a moment balance, and I can say, well, the total force on the plate multiplied by the center of pressure is equal to my elemental or my integral moment on the anti-clockwise, and these two things must be equal, and you can use this equation to work out what the center of pressure is. Okay. So the next thing I want to cover is the force on a curved surface. So theoretically, we could do the same as what we did in the previous couple of slides and define a coordinate direction along a surface and do exactly the same thing that we did before. But that's very difficult, and it's certainly not very general, so it might work for this particular sketch, but it wouldn't work for an arbitrary shaped surface. So a good way to do it for an arbitrary shaped surface is to take a volume of fluid and do a force balance on this fluid. So if we take this volume of fluid next to this curved surface and we make a control volume here, so this A and C and B are here, so this is A and C is here and B is here, and we do a force balance on this fluid. So we've got several forces going on here. We've got forces in the X and the Y direction. So remember, this is a momentum conservation problem without any momentum. So we're going to do a X direction force balance and a Y direction force balance. Okay, so we've got a force acting in the horizontal direction because we've got a pressure distribution on this surface, because there's a column of fluid above here, and that's going to be balanced by the horizontal component of the resultant force on this curved surface. So there'll be a force on this curved surface that has to balance this thing here. Okay, and there will be forces in a vertical direction. So there's a force on this particular surface of this control volume because of the weight of the fluid above this volume, and there'll be an additional force, vertical force, on this curved gate due to the weight of the fluid inside this volume. So there's going to be another vertical component of force that's acting on this gate that has to oppose these two forces, because effectively it's a static problem and all of our forces have got to be in equilibrium. So let's work out the force in the X direction first of all. So that's FAC, and if we wanted to work out an elemental force, that would be PdA, and then we're going to integrate in the Y direction, vertical direction, and we're going to end up working out the net force. So we've got the integral of PdA, so P is rho g of Y, and dA is just delta Y because it's unit width. So dA is effectively W dy, but we're going to assume W is 1, it's unit width. Okay, so we've got this, and then we can integrate this, so we can integrate this over the limits, and effectively we've got this point C is at depth L1, and A is at L1 plus L2. Okay, so we can put the integration limits of L1 and L1 plus L2 into this, and we can end up working out this. And then we can work out the force in the Y direction. So this is the Y component of this resultant force that we're trying to find. and we've got two forces that are relevant. We've got the weight of the fluid and the force acting on this surface. So the weight of the fluid is the weight of the fluid is mass times, the weight is mass times gravity. So we've got the gravity here, and we've got the mass, which is the density times the volume, and this is quarter of a circle, so the area per unit width, if you like, the volume per unit width is rho L squared 2, so L2 is the radius, so this is like pi r squared, and we want a quarter of it, so we divide it by 4. So this is the weight of the fluid, and then the pressure is the pressure times the area, and the pressure is constant all the way along this area. It's just rho g L1, and the area per unit width is L2. So the area would be W L2, and its unit width, so it's just L2. So this is the pressure FCB. Okay, so we can work out our x and our y components, and this gives us the total magnitude of the force acting on this curved plates. Okay, so we also need, as is similar to what we did with the planar surface, we need to work out where our force can be said to act. Where do we put this force to keep our curved surface in place, because it's being subjected to all of these other forces on the other side of its surface? So we do this by doing the same thing again and working out the centres of pressures in the horizontal and the vertical directions. So we need to work out where the x force is acting in terms of, or where the centre of what we're trying to do is we're trying to work out where, if this force is acting on all of these directions and it can be taken to be this particular force, where does this particular force originate in here? Where's the xy origin of this force, where this is the origin and it acts towards this point here? And if we know that, we can work out where this point is on the surface, and that's where we would place our resultant force to keep it there. So effectively we take moments again, and we say that the force in the x direction, which we've already worked out, multiplied by some depth under here, gives me effectively my y coordinate in this little sub-volume. And we can do that by saying, well, we're working out the moments along this surface. So this is p times y times dA, so it's the same sort of thing again. We end up with this integral, and then we put our integration limits in again. This is L1 and L1 plus L2, and we do this and work it out in this way, like this. So this is our total moment, if you like. And if we want to work out yp, we've already worked out f of x from the previous slide, so we can work out our y component of our pressure, centre of pressure location. And we do the similar thing with the pressure in the horizontal direction. So what we're trying to do is we're saying we've got this particular volume here, and where in the horizontal direction, sort of from C, is my is my resultant force said to act to balance all of these things. Okay, so we need to resolve the forces in the y direction multiplied by some deflection here to balance these two things. And we have to work out where these forces are going to act. So the horizontal force is quite easy because this is a flat surface and it's planar and it's horizontal. So we can quite easily say that, well, the moment for this particular force FCB, BC, is going to be acting in the middle of this length between C and B, and since this length C to B is L2, the force is going to be acting at L2 over 2. So that's what we've got here. And for the weight, we have to work out the centroid of this quadrant. So if this was a hemisphere, effectively the weight would act at if you like x equals 0. It would act on this point here, but because we've only got a quadrant of it, this weight is going to act somewhere nearer nearer C than B, because there's more fluid nearer AB than AC rather than B. Okay, so we can work in general. This is the general formula, and to do it for cylindrical coordinates, we can work this out. You can look this up in a textbook, and so therefore we can work out what our center of pressure is in the horizontal direction and give us a location for where this resultant force in the horizontal position will act. So now we've got all of our information. We've done our resultant forces, and effectively we know where this resultant force is going to act. So it's at this particular location here. So this is the deflection from C, and this is the deflection from our coordinate origin y. So we've got xp and yp, and we know what f of x is and f of y. So we know where this force is going to act. We know at which particular point this force vector crosses this curved surface. So if we wanted to create a force to hold this curved surface in place, we would have a force of magnitude F, and we would have it in this particular direction, and we would point it at this particular point here, and that would balance all of these other forces that are acting in this subvolume. Okay, so we've dealt with forces in submerged surfaces and on planar surfaces. With planar surfaces, it's relatively okay. We just do an integral along the planar surface. For a submerged surface, what we have to do is we take a volume where that curved surface is part of the surface of this subvolume, and do a force balance on that particular volume.